Hi everyone, my name is Tejas and I work in the data infrastructure team at Facebook. In today's talk, I'll be sharing my experiences of designing a custom application using Spark RDD interface. So this is the agenda of the talk. I'll first cover the use case where we used Spark. Then I will talk about how this use case was relevant to Facebook, the product, by demonstrating some real-world applications. Then I'll talk about the system before we migrated to Spark. And of course, I'll talk about how the Spark version looked like. Then I'll go into some scalability problems that we faced while migrating to Spark. And one of the key problems was data skew, and I'll talk about how we solved it. And finally, I'll present some performance numbers. So the use case where we use Spark is N-gram language model training. So for those who don't know, language model training is a concept related to natural language processing. So NLP, or natural language processing, is a field in computer science which involves studying the interactions between computers and natural languages. So to explain it in simple words, we human beings learn a language over a period of time, but computers cannot learn languages in the same way as we do. So computers have to be trained to generate a model of a language. And N-gram-based language model is one of the ways to do that. And it's a heavily used method industry-wide. So to give an example, this is a sentence in English, "Can you please come here?" It has 5 words, so that's why it's called a 5-gram. So in NLP, if you have a single word, it's called as a unigram, 2 words, bigrams. A set of 3 words is called 3 grams, and so on. So imagine if you're just given the first 4 words of the sentence, that is, "Can you please come?" And using a language model, a computer can predict that the 5th word in the sentence is "here." So this is done by the language model using some probability statistics. In terms of real-world applications, language models are used for speech recognitions, machine translation. So one of the most common application of language models is text editors. So let's say if you're writing an email or you're writing a document in Word, if you make some grammatical errors or you make some spelling errors, the editor will suggest you that, hey, there's something wrong. And it will not only tell that there's something wrong, it will also tell you what is the corrected way to write it. So that's something that is powered using NLP. For Facebook, this is one of the use cases where we use natural language models. So this was something that was deployed recently, like last year, end of the last year. So the application here is for automatically generating subtitles for videos. So if you have a page on Facebook and you upload a video, our system can automatically generate subtitles for that video. So this is done by extracting the audio stream of the video and then running it against a language model. One other application for Facebook is to find out low-quality pages. So we allow people to create pages for places. For example, you can create a page for Boston City. You can create a page for Eiffel Tower. In some cases, users can create pages for non-public places. So for example, people can create page saying that "my sweet home," or people can create page for any fake location with some wrong apartment number, fake name of the city. And to find such instances manually, it does not scale. So language models help us to identify such cases. So now I'll go into the technical side of things. So before we moved to Spark, this pipeline was powered using Hive. And when I say Hive, this is the Facebook internal version of Hive, not the open source version of Hive. We had forked from open source version of Hive quite a while ago. So this is the architecture of the pipeline. There are blue boxes and the green cylinders. The blue boxes represent a Hive query, and the green cylinders represent a Hive table. So I'll walk you through the flow of the data. So on the left, you see these set of blue boxes. Each one of them, as I said, is a Hive query. And they're reading their inputs from a Hive table. Now, they can read from different Hive tables and filter out some data. And the bottom line is each of these boxes is running NLP algorithm. And the output is a natural language model just for the data that it sees. And as all these jobs finish, you'll have a set of small models generated. And the last step is running an interpolation algorithm. So this algorithm is, again, a Hive query. And it combines all these small models and emits a final giant language model. So this worked pretty good for us. I'll show you the Hive query for this pipeline. So this is what the query looked like for each one of the blue box. So it's reading from some data source. It has some filter. It's distributing data based on a key. Then it runs the transforms, and then groups by on some key, and then writes to a Hive table. So for those who don't know what a transform is, Hive allows you to run custom codes in two ways. One way is to write a Java UDF, and other way is to have any subprocess launched. So in this case, the subprocess for us was train model, and this was written in C++. So for Hive, you can run any, say, a random binary which is written in C++ or Python or even a Bash script. And what Hive can do is it will take all the rows, serialize it to a string, and send it to this process or the C++ binary. The C++ binary will pick this row from its std in and do its processing. And after it's done, it will write the data to its output stream, that is std out. And Hive then picks up the data from the std out, converts it into the Hive row, and sends it to the downstream SQL operator. So as we have more and more applications written which follow the same pattern, we learned some lessons. So we asked ourselves that, hey, is SQL even the right choice to build such applications? So going back, the pipeline looked something like a dozen of SQL queries all over the place. And most of the queries were having the same template. But the only changes were that they were reading from, say, different data source or table. They might have different filtering clauses, or they might be running with some different configuration for the NLP code. And one more thing that we observed is that when our users started off writing pipelines, they typically start with, say, a small SQL query. But as the business logic grew, the SQL kind of expanded to hundreds of lines. So anyone new to the team, if they want to, say, make a change to this pipeline, they have to first sit and understand what this giant SQL means. And even if you make a small change in some portion of the query, for testing that this change does not break anything, you have to run the pipeline from end to end, because there's no way to test a small section of the pipeline. So this was not only confusing for new people in the team, it was also time consuming. One other lesson that we learned that for working with, for trying to train with larger data sets, this pipeline used to take a lot of time. So for scientists who wanted to do some experimentation, waiting for several hours or even for a day does not just help them. So with these observations, we decided to move to Spark. So in Spark, the high-level architecture of the pipeline looked exactly same as it was before. And I'll explain in a second why we did that. So we continued to read from the inputs from Hive, and the outputs were also written to Hive tables. Now, as I mentioned earlier, that we were using transforms, and these transforms were C++ code written by some machine learning experts within Facebook. And rewriting this whole algorithm or logic from C++ into Scala was a significant engineering challenge, or rather, it will take a lot of time. And we decided, let's just stick with the same C++ binaries and try to run the same stuff with Spark. And this helped also in the pipeline migration, because The C++ binaries were not rewritten. We used them exactly as they were in Hive. So for the perspective, for people who wrote for the perspective of the NLP experts, they did not have to do any change. It was a transparent change for them. Since we were using, so one more decision that we made was to use RDDs and not data sets. So back then, data sets was a new concept, and we wanted to have control over lower level stuff. So say, for example, we wanted to write our own partitioner. We wanted to checkpoint at any arbitrary points in the pipeline. So this is something that is easily supported into RDDs. So that's why we went ahead with the RDD APIs. And since we chose to use the RDD APIs, we had to use the pipe operator. For those who don't know, pipe operator is a way which in Spark which allows you to run any arbitrary C++ or Python or any bash command, and it passes the rows of RDD to this process. And just like a Hive transform, your data is transformed by this process, and then Spark reads the output and then serializes into rows and sends to the next operator. So after this whole exercise, we were pretty happy because we started off from a place where the pipeline looked like a dozens of SQL string. And then we went to a place where the code was heavily modular. We had well-defined classes, well-defined methods to do logical operations. And for anyone new joining the team, they could understand it easily. And even changing a code, let's say if you're changing some place in a single method, that involved just testing that particular method, and we had good unit tests for it. So in a way, the development time for the pipeline also reduced. We went one step further and created a service out of this. So inside Facebook, if there are any new applications who want to build language models, they could just provide us with some configurations. So this is what the configuration looked like. And so all this is telling is that, say where the input data is, where should the final output be written, and any Spark-specific configurations or any configurations for the NLP library. And that's it. So for end users, they didn't have to write any SQL after this point. As we tried to use this framework to process more and more data, we ran into some scalability problems. And these are the scalability problems at high level. So as you can see, most of them are around, say, OOMs or GC. And instead of chasing these problems one by one, what we thought that, hey, let's see and understand why these problems are happening. So at high level, we found out that most of these problems are attributed to just one cause, and that is data skew. So data skew is a well-known problem in data processing systems. So whenever you're distributing some data based on some key, and there are a lot of rows corresponding to a particular key, then the node which is processing that chunk of data, it will take a lot of time. So before going into how we solve data skew, I'll first try to describe why we even had data skew in the first place. So let's recap to the previous architecture that I showed. So this is the architecture of the pipeline, and let's zoom into what this blue box is doing. So these are the three logical steps that were being performed. So the first step is extract n-grams and populate the counts for those. Second step was estimation and pruning, and third step was normalization. So I won't go into details about the importance of each step because that would involve explaining the NLP part of things. So instead, I'll show you the flow of the data through each and every step, and then demonstrate how data skew was happening. And by the way, the middle step, estimation and pruning, that's where the data skew was happening. So in the beginning, we have this input data, which is basically a set of sentences in English. And this can be, say, in orders of terabytes. By the way, it's a complex data. And then what we do is that we pick each and every sentence, and we chop it into parts. And while we chop it, say, a single word, 2 words, 3 words, and so on. And then we generate counts for them. So this is kind of similar to doing a word count. except that instead of looking at every single word, we are also looking at group of words. Then the next step is to partition the data. So for partitioning, we had to use the last 2 words in every n-gram. So here I highlighted the last 2 words for every n-gram. And based on those words, we partitioned the data. Now to do this partitioning, we defined our own custom partitioner. And because we use RDD, this was just easy. Now this is how the data look like after the partitioning. So you can see that in this case, there are a lot of n-grams matching with this, and this particular partition has more rows compared to the other one. And finally, we have this special shard called as the zero shard. Now, zero shard is literally speaking a word count. So every word that you encounter in your input, you count the frequency of this word, and we call it the zero shard. In terms of data distribution, when the job ran, this is how it looked like. So the blue vertical strips are shards, and the size of the strip represents how much data it has. And on the bottom, you have this yellow stripe, which is the zero shard as I explained before. So zero shard is the word count, and this special shard has to be shipped to all the nodes. So when we process the data, some of the shards, as I mentioned, had data skew. And this can happen because some of the phrases that are commonly occurring in English can have lots of sentences matching to it. So for example, in English, we can find so many sentences which are like, how do you do XYZ, or how do you do foo? So that particular shard can have a lot of skew. And one of the solutions that we thought about for solving data skew was changing the partitioning in this case. So instead of packing the single word frequencies in this zero shard, what we did is that we also said that let's just have single word frequencies and double word frequencies populated in the zero shard. So after doing this, you can see that the blue shards have a lesser skew, and then this can be worked with. But the problem that we faced doing this was this particular yellow shard that has to be shipped to all the nodes is larger in size. And again, this did not work out for us. The solution that we came up with was something hybrid between both of the things that I talked about. So this is kind of an iterative algorithm. So you first start off looking at all your shards, and then you say, I'll find out all the last shard and just discard them. So this is a rough sketch of how the code looked like. And this is all using the Spark RDD APIs. Then once you discard the skew shard, you only process the remaining shards. After that, you go to the second iteration, and then you look at the remaining shards which are skewed. So we recompute the zero shard this time, looking at only the words in the remaining skewed shard. So the effective zero shard is lesser in size, and now we repartition the shards which are skewed earlier. So now the skew is reduced. There might be still some shards which are skew, and in this round we say, okay, let's just ignore those shards and process the remaining ones. And we continue doing that for more and more iterations until we go to a point where there are no more skewed shards. So this is a high-level idea of what the code look like. It's basically a loop, and then you have some functions, and then you do some operations on the RDD. So the whole point of showing you guys the code is to demonstrate that how easy it is to do such complicated stuff using the RDD APIs. So imagine if you had to do this using, say, writing a SQL query. First of all, it's not possible to do this using SQL. And now on the other side, if you have something like MapReduce, you can do this using MapReduce, but then the effort involved will be quite large. Now, as you can see, this code is pretty neat, readable, and succinct. So finally, these are some performance numbers for comparing Spark versus Hive. So the blue bar is Hive, and the yellow bar is Spark. And I have 2 metrics that I use to compare the performance. So one is the reserved CPU time, and other is latency. Latency is straightforward. Latency is the time taken for the pipeline to run. And the other metric, reserve CPU time, is something that we use internally to measure performance of a job. So to explain, whenever any user hits enter and says, let's run this query, this triggers allocating or reserving some CPU on the cluster. And when the job actually runs on the cluster, the CPU cannot be used by any other job. So only your job can use the CPU. And let's say if the job is not using the CPU, it may be stuck doing some I/O. But still, the CPU is allocated for the job, and no one else can use that CPU. So although your job is not burning CPU cycles, it is still reserving the CPU, and that's why we look at the reserved CPU time, and not just the CPU time. So to give one more example, like externally, when people use Amazon AWS, now you can reserve instance for, say, a day, that is 24 hours, and within a day, say you run your query just for an hour. So Amazon won't look at that you just ran it for an hour. It will charge you for the complete 24-hour period, because that's how long you booked the instance for. So for both these metrics, Spark performed really, really well. And while we worked on this project, we also made a few contributions to the pipe operator, and this has been committed upstream. With that, I'll be happy to answer some questions.
Have you asked the Spark team to also make this available in like the newer APIs, like data sets, so you could like plug in your own partitioner or do more sort of custom stuff like this?
So I think that's a good question. I have not asked about this, but I think the whole idea for data sets is to make writing SQL operations easier. And so these kind of things are, I don't think so they're relevant for SQL.
Sorry, maybe you mentioned this already. What is the motivation for this special partitioning? Why do you partition by the last two words?
Oh, so that has something to do with the way this NLP side of things work. And so as you can see, we only use Spark or even Hive just for distributing the data, or maybe grouping based on some keys. And how the data is distributed and the requirements around it was governed by the NLP algorithm that was written by some experts. So, I mean, to explain that, I'll have to go into NLP side of things, which I don't think is relevant.
Okay, so you talked about skewed distributions. But I'd like to ask about, did you use any sort of smoothing the language model, like neither Bay method or white bell or something? Because as I understand, those are like some simple statistical method which also deal with this very skewed distributions. Like as I understand, correct me if wrong, they are used to modify like the frequency counts, especially for very infrequent terms, or like 2 grams or 3 grams or whatever.
So we did apply some smoothing techniques, and despite of that, we had the data skew. So if you want to read more details on that, actually I published a blog about this on the Facebook engineering page. So in that I mentioned about smoothing. So okay. You can read that paper.
Okay. Another thing, I know it might not be related, but for example, in speech recognition, I've been using even the n-gram itself, but now there is like a recent trend to replace the n-gram with the recurrent neural networks.
Sorry, with what?
Replace the n-gram model with recurrent neural networks.
RNN.
So I'm not sure. Is there like a tendency like also to have some work on that? Like, because also I think they will be more useful for, instead of having like an up to 5-gram models, to have just a recurrent neural network. Maybe it will be like less computationally expensive.
We can talk offline. So
Okay.
actually, yeah, we had discussed RNN versus this approach as well.
Okay. All right. Thank you.
Hey, great talk. Thank you. My question is why, so I completely understand for the custom partitioning and that sort of thing, but is there any reason why you didn't necessarily use sort of Spark SQL upstream and then basically just repartition it when you actually do that? Basically, why did you end up keeping the Hive jobs involved in the first place? Does that make sense?
No, I did not understand the question.
Yeah, so you use Hive, and then you do that sort of RDD transformation, right? And then
Yep.
you output another Hive table.
Yep.
Is there any reason you didn't just use Spark SQL, then RDD transformation, and then Spark SQL to the output table?
Oh, so if I go back, so there were two main reasons. So one was we didn't think that SQL is a right choice to do this. So yeah, these were the two main reasons. So first of all, like let's go back to what I said. So if you stick with SQL, the pipeline was like you'll have dozens of SQL statements in the code. And most of the SQL statements were kind of similar. So they might be reading from different data sources. They might be using like different filtering or different parameters. But the structure of the query was kind of the same. And for anyone new to the team to understand the whole SQL thing will take a lot of time. So when the pipelines are originally written, our users had, say, small queries, 10, 15 lines. But as the business logic grew, the SQL just exploded to hundreds of lines. And other reason was we could not do any custom partitioning if we just chose the SQL route. So for training with larger data, that wouldn't have worked. So even with Hive, we faced the same problem. That's correct. So we use Hive just for, say, storing inputs and outputs.
Thank you for the talk. That was great. So when you have a pipeline, you ideally want to run it all in the same, same run. But when it's dealing with big tables, probably you want to do intermediate checkpoints. So I was wondering, how do you do that with RDDs? What's the approach to persist the data, or when you do it? Could you please elaborate a little bit more on that?
So I think with RDD, there are APIs to save object to file. I think there's some method.
Yeah, there is. Okay, so
that's what we used.
Okay, so that you have to name it and then load it back again, maybe.
Yeah.
Because there is also the checkpoint method that you can use, but that one it's not in the lineage, right?
Yeah, we didn't end up using that. So the checkpoint method, we did not use it. We used the save object method.
And a reason for that?
I actually don't remember at this point.
But you don't. Okay, that's good enough. Thank you. Thank you.
Okay, thank you very much. Please show your appreciation.